Today we will study Jablonski diagrams. Jablonski diagrams are very important diagrams to understand fluorescence behavior, to get the insight of how the transfer is taking place in the fluorescent materials. It consists of many energy levels and possible vibration levels and transition between them. In the previous lectures, we have discussed vibrotic interaction, Hertzberg-Taylor theory, fluorescence spectroscopy, Kasha's rule. Then we have discussed quantum field, radio transitions. Now we are discussing Jablonski diagrams, the diagrams for fluorescence spectrum. At the end of this lecture, you will learn how to create Jablonski diagram, what is the meaning of different levels, what are singlets, triplets, how transition takes place between them, and how you can get the idea of energy levels, and finally some applications. We have discussed transitions in the previous topics, and it is true the radiative transitions involve absorption of photon. If the transition occurs to a higher level or the or emission of a photon for a transition to lower level. So basically any transition, radiative means it radiates, it gives emissions. In any emission, this involves two processes, absorption followed by emission. In the case of absorption, the transition occurs from lower level to higher energy level by some way. Most of the time either heat or light, and then this event is followed by emission of photon, in which the transition occurs from higher level to lower level. The name how we have this name Jablonski. Jablonski basically a professor, Professor Alexander Jablonski. He is regarded as the father of fluorescence spectroscopy, or the flag bearer in this field. And to respect that, we have given the name of these diagrams as Jablonski diagrams. Jablonski, who is regarded as the father because of his many accomplishments, including description of concentration, depolarization, and defining the term anisotropy to describe polarized emission. Jablonski diagram often used as starting point for discussing light absorption and emission, and are used in a variety of forms to illustrate various molecular process that occurs in excited states. In molecular spectroscopy, a Jablonski diagram is a diagram that illustrates the electronic state of a molecule and transition between them. The states are arranged vertically by energy and grouped horizontally by spin multiplicity. Non-radiative transitions are indicated by squiggly arrows and radiative transitions by straight arrows. You can see here, dashed or full lines. The vibration ground state of each electronic states are indicated with thick lines. The higher vibration states with thinner lines. The diagram is named after this Polish physicist as Alexander Jablonski. In the insert, the photograph is shown of Jablonski. The figure lower is given. Here we have various energy levels and the tension between energy levels. Of course, the energy levels are different here. S0 is different, S1 is different, S2 is different, T1 is different. This is based on their multiplicity and spin behavior. A typical Jablonski diagram is shown here. First one is singlet ground as S0, then first singlet, then second singlet, S0, S1 and S2 respectively. Here this is S0, this is S1 and this is S2. At each of these electronic levels, the fluorescent phosphor can exist in many vibration levels. This is electronic state S0. Then in this state, we have several vibration levels. These vibrations can be shown here, this is here, and this is here, or here. The transition between states are depicted as vertical lines to illustrate instantaneous nature of light absorption. The transition occurs about 10 to 15 seconds, a time short for significant displacement of nuclei. This is Frank-Condon principle. Here it is shown when you give energy, move to excited state. Then after this, they move to ground state. It's called internal conversion. And finally, the emission takes place from the lowest energy level. This is called fluorescence. However, this is fluorescence. However, in phosphorescence, there is a possibility that these electrons may also move to triplet states. And then we have discussed these things in the past classes, so you can go through this. At room temperature, the thermal energy is not adequate to significantly populate the excited vibration states. And absorption and emission occur mostly from molecules with the lowest vibration energy. We have discussed this rule in the previous lecture also. So you can get the details from there. The larger energy difference between S0 and S1 excited state is too large for thermal population. This is the reason why we use light, not heat, to induce fluorescence. A phosphor is usually excited to some higher vibration levels of either S1 or S2, with a few rare exceptions. We give the energy and move to excited state, either S1 or S2. However, in few exceptions, the molecule in condensed matter phase rapidly relax to the lowest vibration level of S1. First, they move to S1 and S2, then they move to from S2 they move to S1. This process in which it moved to lower state is called internal conversion. In internal conversion, there is no change in singlet state. They just transfer their internally, they just really internally adjust this thing and move to ground state. These are not radiative tensions. Since fluorescence lifetime are typically 810 to 8 to minus 8 seconds, internal conversion is generally complete prior to emission. In this time, it will complete, and the fluorescent emission generally result from thermally equilibrium excited state, that is lowest energy vibration state of SN. 1. The non-radiative transitions arise through several different mechanisms. One is called vibration relaxation, in which relaxation to excited state to its lower vibration state is occur. This process involves dissipation of energy from molecule to its surroundings, and thus it cannot occur for isolated molecules. So one thing we should realize, then one is relaxation is possible through vibration relaxations, but in this the important thing is this is possible only with dissipation of energy from the molecule to surroundings. If there is no surrounding, this cannot happen. Surrounding is so even we can check the we can characterize the presence of surrounding by observing such type of relaxation in any system, in any place. Second type of non-radiative transition is internal conversion, which occurs when vibration states of electrically excited states coupled to vibration state of low electronic states. Internal conversion. In this, vibration states couple the vibration state of lower state and transfer the things internally. Third type is called inter-system crossing. That is the transition to a state with different spin. As we are discussing several times, whenever we give the energy, we move to singlet state. Now, if there is a possibility of triplet state in the system, then this internal system may occur, in which the transition takes place with a different spin multiplicity. In molecules with large spin orbit coupling, inter-system crossing is more important than molecules that exhibit only small orbit coupling. Inter-system crossing can be followed by phosphorescence. Yes, The ISC or inter-systems crossing is responsible for phosphorescence, whereas IC is responsible for fluorescence. The spectrum that we obtained is typically a mirror image of absorption spectrum of S0 to S1. And this similarity occurs because electronic excitation doesn't greatly alter the nucleic geometry. Hence, the spacing of vibration energy is similar to that ground state. As a result, the vibrational structures seen in the absorption and emission spectra are similar. Molecule in the S1 state can also undergo a spin conversion as we have discussed and move to triplet state also. We have discussed this thing in detail in the previous slide. As we have told, the emission from T1, if somehow due to intersystem crossing, the electron move to triplet state, then there is a possibility that they are shifted to longer wavelength related to fluorescence. Conversion of S1 to T1 is called intersystem crossing. Translation from T1 to singlet ground state is forbidden, and as a result, the rate consists for triplet emission are several order of magnitude smaller than fluorescence. Molecules containing heavy atoms such as bromine or iodine are frequently phosphorescent. The heavy atom facilitate intersystem crossing and thus enhance phosphorence quantum yield. So that is again important thing here. The heavy atom gives the phenomena of phosphorence. We should learn these things, how bromine and iodine give phosphorence. This graph diagram is again given to you for practice. You can practice these things. Absorption is there, emission is there, fluorescence called, then non-radiative transition is there. And also mention this, also see that clearly the difference between the levels is decreasing as you move away. Also remember why the lower level is dark, bold. We have discussed these things. Just try to remember these things. What is S0, what is S1, everything. Again, I have shown this for practice. Schematic of transition of electron states of a molecule during fluorescence phenomena. The left axis shows increasing energy, where a typical fluorescent molecules has absorbance spectrum. The spectrum shows energy or wavelength where molecule absorb light. If the incident light is at wavelength where the molecule will absorb the photon, the molecule is then excited and move to higher energy state. Here we have shown many things. From ground state, you give absorption, then absorption say to, we have some transition from S2 to S1. First, it is shown you the absorption, then emission will take place, and emission is shown from singlet state to ground. We have also shown here heat loss to environment and then intercrossing system here. And if it recursion occurs, we also have phosphorescence of microseconds. So many things are shown here, and it is always needed whenever question is asked in the exam. You have to draw the figure and discuss various parts of this figure. Thank you. In this lecture, you have learned Jablonski diagram. Try to prepare the Jablonski diagram and analyze what is S0, S1, S2, then various transitions, radiative, non-radiative, then fluorescence and phosphorescence. Just by a single figure, we can explain many things about fluorescence. Thank you and take care.